Hi, so today we are going to take a look at this problem, the kth smallest element in a sorted matrix. I encounter this problem when I'm working on the top interview questions list. And you can see that there are many up thumbs. So it seems to be a good question here. So it says that you are giving a matrix which is a square, and for each rows it is sorted, and for each columns it is sorted too, but you cannot make sure that for example here in the first example you can see that 159 is sorted, 10, 11, 13 is sorted, but you can see here 12 is not larger than 13, but in the first column it is sorted. So it is a matrix like this, and you need to return the kth smallest element in this sorted order. And you need to notice that it's not the kth distinct element. So for example, if here we have some elements, redundant elements in this matrix, you need to count them. Okay, and also you must find a solution with a memory complexity better than n squared. That means that because in the brute force way, we can just take all the elements in this matrix and then sort it and return the nth element. But if we do that, we will have a memory complexity because we need to record all the elements in the matrix. So we cannot use brute force way. Okay, and when it comes to get the k smallest or k largest element, the first thing we can come up with is to using the heap, because using heap you can dynamically maintain a list which is sorted, and for each insert or each pop it calls only log k, for k means that the length of the heap. Okay, and another one, to find a specific element in a sorted array, we can think that it might be solved by the binary search. Okay, because for the binary search it usually calls only log n. Okay, so let's first take a look at the solution in the heap. So we need to import the heap queue. Okay, how do we get the kth smallest element using heap? Here, let's look at the example again. So one thing we know and certain is that every element at the beginning of every row will be the smallest of that row, right? And so that will be our first thing to put into the heap. So, and And also we know that in each row the numbers are sorted. So if we want to find the next smallest element, we need to find the smallest element in the first column. So there, for example here, 1 is smaller than 10. So it has higher possibility that the neighbor of 1 is also smaller than 10. Like, because we will not look at 10 first, because the neighbor of 10 is 11. It will larger than 1, right? So there is no way we can find smaller elements. Okay, remember our goal is to find a smallest elements here. For example, if k equals to 8, but currently if we only take the first column, we only have length of 3. That means we need to find 5 more elements that is small, so that we can find the target. Okay, so first we need to record the first column. We need to push the first column into our heap, and then we pop the smallest one and to check its neighbor, and then we always pop the smallest one to find its neighbor until we met the k element. So okay, let's and in this algorithm, let's take a look at the time complexity. First of all, we will at first we need to push the first column into our heap, and this will make on, and then we need to operate k steps. So basically here we will do like k. We need to do k operation to find the k smallest element. And for each iteration, what we will do is to pop the current minimum and then push its neighbor. So for pop, it will be O of k, then O of log k, and then push again equals big O of log k, because the length of the heap will be at most k element. I think it's at most an element, because at first we will push the first column into the heap, and the length of it is n. So at the beginning, the length of the heap is n, and then every time we will pop one element and push one element, so the length of the heap remains n. So here is log n. So the overall time complexity here will be k multiple log n. So the overall time complexity, here we can see that k will be smaller than n squared. So k might be bigger than n. The overall will be O n plus k log n, which is dominant by k. So it's k log n. And k is n squared. Okay, this is the time complexity, but the constraint said that our memory complexity need to smaller than O of n squared. And here, our we need to maintain the heap, right? And the length of the heap is n. So the memory, the space complexity is O of n, and this fits the constraint. So let's finish the code. First of all, push the first column into the heap. Let's first check the length of the matrix and put n here. So let's initialize a heap. Let's call it Q. Let's call it heap. So heap, and we record the element, and also we need to record the coordinate, like the row index and the column index, so that we can find the neighbor of it. Okay, and here we pop the element. So let's make it current, and the row, the column. And then we push the neighbor. But what if there is no neighbor? Like when we already met this one, when the current element is this one, there is no neighbor of it, right? So we just skip this row. We didn't. We will not push any element into the heap. So let's make sure that the column is smaller than n minus 1. Smaller than n. It can be n minus 1. So if this constraint is satisfied, then we push the neighbor of it into the heap. we know that when the kth iteration, the answer will be the correct because it's the 8th element that is popped out. And also, I think we can deal with some edge case here. For example, if there is only one element in the matrix, and also k is 1, we can directly return the only element in the matrix. Okay, let's see what happened. Okay, oh, here. Okay, this here needs to be -1 because we will we want to record the neighbor. So we only record neighbor if currently we are at the very we are not the end of the array. So here should be -1. Okay, let's submit. Yay, finish it. Okay, and then next let's look at another method, which is binary search. Actually, the binary search solution is more of normal way that, more usual way to solve this kind of problem. Like in an algorithm course, the teacher will teach you to use the binary search method because when using binary search, you don't need extra space, so you can fit the satisfy the constraint here, like the follow-up, to solve it with O1 memory complexity. Okay, let's do it. How to use binary search. So let's again take a look at the example. So if we know we want the 8th element, then we know that it must be between the smallest one and the biggest one, right? And we know that the smallest one is this one, and the biggest one is this one. And our answer is among between these two numbers. So we can use binary search to search the range from 1 to 15, like the smallest to the largest. And how to check if I found the answer? So basically, if we if we find a number like 12, okay, how do we know that if 12 is the kth smallest element or not? That means that in the array there are 7 elements that is smaller or equal to this one, right? So if we can count the number of the element that is smaller or equal to the number, then we can know if it is an answer or not. And how can we count the smaller or equal number, the sorted feature can help us. For example, how can we know how many elements are smaller or equal to 12? First, we can take a look at the first row. If we know that 12 is larger than 9, what does it mean? That means that all of other elements are smaller than 12, right? So we can directly add the count to 3. That means there are 3 elements in this row that is smaller than 12. And let's move on to the next row. So is 13 smaller than 12? No, it's larger, right? So we just move backward for one step. Is 11 smaller than 12? Yes. So that we know that in this row there are 2 elements that is smaller or equal than 12, and so on and so on. So in the third row we can know that there are only 1 element that is smaller than 12. So in this way we can count all the elements that is smaller than 12, and it's more efficient to count it one by one. Okay, so that's it. That's the basic idea of the solution of binary search. For the time complexity, first of all, the binary search itself will cause O log n, where n means the largest element. So let's just call it m. Okay. Here n means the largest element in this array, in this matrix. Okay. And but inside every iteration of the binary search, we need to count how many elements are smaller or equal to the matrix, to the element. So that might cost big O of n square. Well, it let me think. If, for example, if there is only 1 smaller here, for example, if we are looking at, let's change the element here. So we are looking for 11. So in this row, we know that there is only 1 element is smaller. Do we still need to look at the beginning of the next row? I think we still okay, let me think. This one is smaller than this one. So this one is bigger than this one. So if it is smaller than the target, if it is larger than the target, then this one must larger than the target. So next time I just need to check if this one is smaller or equal to the target. So okay, let's just call it big O of n squared. Okay, so the total time complexity will be big O of n squared plus multiple log n, and the space complexity will be O1 because we don't need to restore any information. We just need to perform the binary search. Okay, so let's start coding. So L and R equals to the smallest and the largest. And while and okay, and so mid is so we need to write an additional function for us to count the number of the elements that is smaller or equal. And the input is a number. Let's skip it for a second. So basically you will count the number, and if it is smaller than k, that means there is still not enough element on the left hand side. So we need to look at the right portion of that. So we need to move the L pointer to the n plus 1. Also, we need to use an ANS answer to record what we've already found. So if it is larger than k, that means we need to look at the left part. So R equals to minus 1. Also, we need to record this one. Okay, and now let's move on to count smaller or equal here. So C equals to So we need to count the numbers row by row, and for the first row, we need to check if the rightmost element is smaller than target or not. If it is, then we can directly add count to n. And if not, we need to move to the left to find the first element that is smaller than the target. So the while would be if the element is still larger than the target, we just need to move the element backward. And when we found an element, for example, we stop at the second element this time, and when we move to the next row, we can start from this element, right? So here we put the C in outside the for loop, so that we can reuse the C to the next iteration of the row. Okay, so when I found one, we count C plus 1. Okay, let's see. What's wrong with that? Oh, this should be M. Oh, okay. Here we cannot keep move C toward left because C needs to satisfy this one. Oh, typo here. Okay, let's see if it is correct. Yeah, this is correct. Hooray! Okay, and there is a trick here, like why do we need to use answer to record it? Why don't we directly return the M when the while loop is M? Because that if we return the element we first match this constraint, this condition, let's not always be the answer. Because, for example, here, if there are there are multiple elements that is the same, and we didn't meet the we cannot make sure if it is the right element we want to find. So we need to find the smallest one of the element that we want. Okay, so that's the solution for this problem. So basically, heap solution is more intuitive and it's easy to implement. But using binary search, you can have a better memory complexity because you don't need to restore a heap. Okay.